Hi everybody, I'm going to review with you three-phase circuits, how to calculate the power, complex power, active power in three-phase circuits. And we're going to have one example that about one load connected to a transition line to a source. And in another video, we're going to explain how we can calculate the power for two loads connected in parallel to one system. So let's just start. First, let's say that you have the reference here on angle 0 and you have a voltage V phi. It means, phase voltage, and the angle is theta V, and you have the current I phi. That's the phase current, and it's angle theta I. So the phasor of one phase voltage is equal to the magnitude of the voltage on angle theta V voltage, and the current of one phase, that's the phasor, is equal to the magnitude of the current of one phase and the angle theta I. Remember, V phi and I phi in this equation, they are root mean square values. Okay, so how can you find the complex power for one single phase? You multiply the magnitude of the phase voltage times the current of one phase, and the angle is equal theta. What is the angle theta? Theta is the difference between theta V minus theta I, the difference between the angle of the phase voltage and the angle of the phase current. And always we're going to use in the common discussion this notation. If you express this equation in rectangular form, so you have V phi times I phi cosine theta plus J V phi I phi sine theta. This will be the active power of one single phase, and that will be reactive power of one single phase. Okay, somebody will say, but you're supposed to find the complex power for the three phase. Easy. If you want to find three phase complex power, you just multiply one single phase by 3. In other words, would be equal to 3 voltage, like this expression, times I phi and the angle theta. Somebody will ask, you still using the angle theta that you use for phase with the line? Yes. There is nothing called the angle between line current and RM. Yes, maybe there is but we don't use it in the expression for the complex power. If you analyze that, you will have 3 V phi I phi cosine theta plus J 3 V phi I phi sine theta. So that's going to be the power or active power of three phase, and that will be the reactive power of a three phase. You can compare everything. The three phase power, it's equal just 3 times a single phase. Okay, easy. Well, somebody may ask, can I use the values of line voltage and line currents? Yes, you can. If you want to do it, so the complex power will be equal to, instead of multiplying 3 by V phi I phi, you will multiply square root of 3 V line, I line magnitude, and the angle theta, the same angle used with phase. Yes. And if you do that, you will have square root of 3 VL IL cosine theta plus J square root of 3 VL IL sine theta. Another expression for the active power for three phase, another expression for the reactive power Q for three phase. Simple. Great. Well, so let's just now solve one example. Let's read this example. Well, a balanced three-phase load requires 480 kilowatt. At a lagging power factor, 0.8, the load is fed from line having an impedance. Okay, so there is a transmission line, and the line voltage at the terminals of the load is 600 voltage. All right, so you can say in general, if you sketch it, because I mean we want to find like equivalent one single phase. If we look here, you see construct a single phase equivalent circuit. So they didn't mention anything, so I don't know it's delta or Y, so I will consider it Y if nothing is mentioned. So I'll find the equivalent single phase. So I will have like one source. I will just do it like that. That's the source. All right. And I have a load on the other side. And I will just represent by impedance. And I connect the neutral. Oh, yes, this is the neutral. And then I connect the phase here or the line, but I will connect through the transmission line. So the small letter stand for the source, AN, and the capital letter stand for the load, capital A, capital N. And I start to put the information. That's the transmission line was giving the impedance. The impedance of transmission line is equal 0.005. It means the resistance. So let's just move this a little bit up. Oops. All right, so it's equal to 0.005. That's the resistance plus J. It's given here, let's just make it clear. Okay, 0.025. Oh, remember what I'm doing, it's equivalent. Single phase. Only single phase to represent three phase. And the impedance of the transmission line is given per phase. You see, ohm per phase, so I'm fine. But the load is given for a three-phase load requires 480 kilowatt at lagging power factor 0.8. So this power for a three-phase, and I'm using single phase, so I have to convert three-phase power into single phase. Again, yeah. What's given in the problem, the power of a three-phase is equal to, that's given here, 480 kilowatt. At power factor 0.8 lagging. Okay, so what do you need? What? I first have to write the information here. This information of the load, I just write there, 480. Oh no, that's a single phase. So what should you do? You got to convert this into one single phase value. How you find that? It's easy, you remember? Three phase is equal 3 times single phase. So the power of one phase is equal 480 divided by 3, which is equal to 160 kilowatt. The power factor doesn't change, by the way. You don't divide it, not ever. So you have 160 kilowatt. And the power factor is 0.8 lagging. So everything is given. No, I forgot to put the voltage here. Across the load is given 600 volts, but this is line voltage, and we assume it's star. So you get divided by, so you write the voltage of AN magnitude, it should be equal 600 divided by square root of 3. We're assuming it's Y, and that's the relationship between the voltage and the current. All right, so that's the value for the voltage across only one phase. 600 over square root of 3. All right, you don't have to find the value, you can write like that in volt. All right, and you might even assume it's the reference. So if you want to write the phasor, you'll write VAN is equal to 600 divided by square root of 3, and the angle is 0. Take it as a reference. All right, and voltage. So you write here that's equal 600 divided by square root of 3 voltage. So we have the all information. Yes, we do. The information that's given, it's already expressed in this diagram. So what's next? Next, we did A. We construct a single phase equivalent circuit. The second part, calculate the magnitude of the line current. Line current, yes. But you said you're doing equivalent single phase. Yes, but the line current and the single phase are the same in one star, right? That's the line current and the same as the phase. And how you call it? I going from A small to A capital. That's the phase and line at the same time. Oh, so how can you get it? How you calculate it? Well, remember, current, there are many relationships. You got to think about it, because if you have this question, I mean, how you answer it? Well, current can be calculated if you know the voltage and the impedance, right? But you don't know the impedance here. Z is not given. So it's not going to work. What else? What other relationship? Oh, there is a relationship between the complex power S and the current. S and current, there is a relationship. What relationship? I just reviewed with you in the beginning of this video. Here you go. That's if you're working with three phase. And that's if you're working with single phase. So that's, I mean, S phi is equal V phi I phi on angle theta. And if you take only the magnitude, because you call this complex power, let's just let complex power. But only if you talk about the magnitude, you write S without anything like that, it's V phi I phi. Great. So this is a useful relation. So I'll say S phi for one single phase is equal V I. And now I'm talking about the phase V, A capital N, and I, A. That's the magnitude. That's the apparent power. Well, do you know the voltage? I know the voltage. Yes. Do you know S? No. Do you have information to help you to find the S? Yes. What information? I have power and power factor. Well, how does this help? Well, do you remember? There's something called power triangle. Okay, let's just try to make it nice. Power triangle. All right. Yeah. Oh, this is the triangle. Here is the power, Q, S, and angle theta. Can you just write some information about triangle? Oh, yes. First of all, power factor is equal cosine theta, and at the same time is equal P over S, because cosine theta P over S. And because of Pythagorean, you have S squared is equal P squared plus Q squared. So this is the information that you have. You can get anything else you see using trig. Well, don't lose me. I want to find S. So what's given here? Power. Power per one phase 160 kilowatt. All right, 160 kilowatt. And power factor 0.8, lagging. All right. So what can you do now? Well, I can use power factor equal P over S and find S magnitude. All right, good. So you have power factor equal to P over S. Power factor 0.8 is equal power, which is equal 160 kilowatt divided by S. Now we can find S. Apparent power is equal 160 divided by 0.8. That would be equal to 200 kilovolts ampere. Now can you find the current? Yes, you can. Use this equation. S is equal to 200, and that's kilovolt ampere, so multiplied by 10 power 3 equal the voltage VAN. What's VAN? It's here, the magnitude 600 over square root of 3 times the current, line current from A to A. Yes, magnitude. So if you do that, you can find the current, IAA magnitude. You divide 200 times 1,000 divided by 600 divided by root 3. What you get 7.35 N. That's the magnitude. Okay, what do you mean the magnitude? Means any phasor has magnitude and angle. So how can you find the angle of the current? Well, do you remember? First, when we did the expression for the current and the voltage for the single phase, we said that the angle of the voltage, angle of the current, and theta, that's related in S, theta is the difference between the voltage angle and the current angle. Oh, all right. Do you have theta? We have theta here, the voltage angle, but we don't know it. But we have the relationship between power factor and cosine theta. So what should you do? Use this formula. Power factor is equal cosine theta. Power factor is equal to 0.8. Replace it 0.8. 0.8. And cosine theta, now you can find theta is equal to cosine minus 1.8. What you get? Well, you get 36.87 degree. But this is theta, not theta I. All right, we know that theta is equal theta V minus theta I. Now we know theta. You don't know theta V. We say, well, we want to take it as a reference. So what's left? Theta I. So we'll find theta I simply is equal negative 36.87 degree. Actually, you can do it from the beginning without doing all that, but just as like an interview for you, how you do it if you have some complex problem. Because, I mean, you know that the voltage is in angle 0, and you have the current lagging. How do you know the current lagging? Because it said the power factor lagging, 0.8 lagging. That's the meaning of lagging. So the same theta would be the negative, the value of theta. Now we mentioned something about power factor lagging. Yes, this is very important to know. If the power factor is lagging, what does it mean? It means Q is positive, and the current I lags the voltage V, like in this situation. If the power factor is leading, what does it mean? Q is negative, and the current leads the voltage. All right. Now we got the angle, negative 36.87, and we got the magnitude, 577.35. So now we can write I phasor for the line is equal to the magnitude 577.35, and the angle negative 36.87 degree, and the unit is amp. And that will be your answer for part B. All right, let's just go and see what's next. We did that part. Oh, calculate the magnitude of the line voltage at the sending end of the line. Oh, so do you want to find VAN? VAN. Oh, let's just write here. That's the one, right? VAN. But you will say that this is phase voltage. It's a single phase equivalent. Yes, I know. But just first find the phase, and then after find the phase multiplied by √3, you get the line. No problem. All right. So how we do that? Well, the voltage at the source is equal to the voltage at the load, which is given, plus the drop across this one. It's just a very simple thing. If you want a voltage to the source here at this side, so the voltage here is equal the voltage at the load plus the drop. So VAN is equal 600 over radical 3 plus the current IA that we got times this impedance. Okay, what you'll get? You get VAN, the phase voltage at the sending end. So let's do that. Now, all right. The voltage, that's part C. The voltage at sending end is equal to the voltage at the load, AN, plus the drop across the threshold line. Okay. Let me sketch for you here. I mean, to know what we're doing. That is the threshold line impedance, and this is the current IAA, and then you have the voltage at the load, VAN, and VN capital, and it's required to find the voltage here, VAN. A small, N small. That's the equation. And use the phasor. Do you know everything? Yes, VN, we got it. VN, let me just refresh your memory. VN, we got it. Where VN? Yeah, that's VN. 600 over square 3 angle 0. So that will be 600 over I got 3 angle 0 plus ZL was given 0.005 plus J 0.025, and the current we just got it in front of you here. That's the current. That will be time 7.35. Just let's move this one here, have space, and the angle is equal to negative 36.87. Use your calculator or MATLAB to do this complex calculation. And okay, be equal to 357.51, and the angle is equal 1.57 degree volts. I advise you to solve this problem by yourself using calculator MATLAB to check the number and also to review. Now you'll tell me that you got VAN small, which is the phase. I want to find the line. That's okay. The line voltage will be equal to the phase voltage times square root of 3. So square root of 3 times the value that we got, 357.51, 157 degree. So if you evaluate this, you'll have 619.23, and the angle is 1.57 degree voltage, and that will be your answer for this part. And that's it. So I think we did finish the problem. Let's check. Yes, we're done. We're done. So that was a simple problem, but I mean, you got to let me add. I will add another one. Let me add just another requirement. Let's say, what about if you are asked to find the power factor of the sending end of the line. What does it mean? It means you know the power factor of the load, but it's very important also to know the power factor at the source, at the sending end. We call the source sending end. So how you can find the power factor? You got to know the angle between the voltage VAN and IAA, because the current coming out the source, the same current in series, it's the same IAA. So the angle between IAA and VAN, that angle will be theta, which will be the and find its cosine. That will be the power factor. Then you will ask, I'm going to use the line values or phase values. Of course, phase values, as we said before, you cannot find power factor for line, I mean just for phase. Do you know the angle of VAN? Yes, we got it here. So that's, oh, that's the line. Oh, what's the same line? This is VAN. Here you go. VN, the angle is equal 1.57. So right, theta V is equal 1.57. What about the current? The current is series, the same current. This is the current, minus 36, right? So theta I is equal negative 36.87. So at the sending end, theta is equal theta V minus theta I. So it'll be 1.57 minus negative 36.87. You get 38.44. So the power factor at sending end, not at the load, equal to cosine the angle theta. Okay, we call it sending end theta S. Okay, so cosine 38.44 you'll find is equal to 0.783, but it's not right. You should write lagging or leading. How you know lagging, leading? You look for the theta. Is it positive or negative? Positive, so you write lagging. Wow. okay, directly. All right, thank you for paying attention, and that was really a good problem. I hope that you got it. See you in another video.